was not giving the best, but we compared between the two. But you have to choose for a ligand where you have a series of compounds, all should be structurally characterized, and you will be able to do comparative study to pinpoint the role of metal ions in doing hydrolysis. That was our target. And then we chose this ligand, which was actually between the two, this was not that good, the other one was better. We took this ligand and we made a bunch of compounds, manganese, cobalt, zinc, also made copper. This should be copper. You know the same thing, same story, acid and bridge. Same story, acid and bridge, so both are very nice. Then we have that, again nice, the same thing. What kind of things are there? Acetonitride. And our condition will be such, this fellow and that fellow will become water after some time, and these acetates will be gone. So each and every compound is isostructural. So everything structurally characterized, isostructural, condition is well established. That was our target. And this is the last edition this year we have published. We did the initially what we did not have, we have manganese, cobalt, zinc, and previous one had nickel. But copper was missing. Copper was giving real trouble in copper. But finally we got the copper. So you know the crystallography, Dr. Malla Reddy is here. When it's crystallized, there could be in the asymmetric unit more than one molecule. So this molecule has two molecules in the asymmetric unit, independent cations. And what you have here, you see here, and this molecule difference is this molecule has one coordination which is nothing but an acetonitride which this one doesn't have. Otherwise the same thing. It gave a little bit of problem in the England, Royal Society crystallography disorder problem, 2.75, 0.5, it was a little bit mess. But we could do it. So we have the same kind of thing all over the place. So we know the conditions from our previous work. Now we have at hand manganese, same thing. Manganese, cobalt, and nickel we had previously, copper and zinc. Now do the same thing. Now I will not repeat the same experiment again and again, I will give you the data. So this is the sum of the substance. So you have manganese 2, these two fellows are acetonitride, cobalt, again acetonitride, nickel, one methanol and one water, the paper I showed you. Copper, nothing is there, only 5 coordinated, and zinc, acetonitride. So more or less same structure, and we have a condition set. We know how to determine potentiometric titration. We know how to determine the pKa from rate constant. So rate, mechanism, activation parameters, enthalpy, entropy, everything we can do, and the exostructure also. So we did that, and again the same story. This thing gets liberated. You have water, and this is your A. That is water weight, and weight will C. So 3 species in solution. Then this is again to remind you it attack and that kind of formation. I am not showing the data again. And conditions I have already mentioned that this is the way you can have the condition of by which you can determine everything. So skip it. So there is no point. The same story, you have the same, you have a condition pH and how it increases. Increase the pH and the K-ops increases. That means there is a pH dependence of the reaction which should be there, because water will become water weight or becomes weight, which is a pH dependent species generation. So that species which is more nucleophilic will be able to do the hydrolysis. So this is understandable, should have happened, and it did happen. Then we did the values now. You know manganese, cobalt, nickel, copper, zinc. pKa you see this, pKa to C and K2 values you see. What you see now, the most importantly you see that this nickel is 7.95 and this is very poor. So nickel is the worst under the conditions, and the pKa of this and that is much higher than others. And you will be surprised to note, in nature, urease gets hydrolyzed around 8 pH, not at 7. So urea gets hydrolyzed at a higher elevated pH. Why? Because nickel is such a metal ion, because the enzyme has nickel for other purpose, and the nickel and water bond is such that it is not that acidic. But zinc and copper, you know, zinc and copper bonds are pretty acidic compared to these 3 metal ions. Now and you see comparable values also. Now the question is, why then nature had gone for zinc, why not copper? So there will be one answer which is called the rule of abundance. Which one is readily available? Nature would always go for. And copper can complicate your reaction by taking part in redox processes, which you don't have in zinc. So we could see that decrease and the best is zinc and copper is also comparable, and then all the details are written here. Now you see this is the order we observe. Nickel is the worst, best is copper and zinc, then cobalt, then manganese. And you will be surprised, all zinc containing enzymes, not synthetic compound, all zinc containing enzymes can be reconstituted by cobalt, and they will maintain their catalytic function or functional behavior. So the functional property, and you can see why it is that zinc and copper, they are next to each other. And the values will be not too bad between zinc and these values. You can check it. The values are reasonably okay. You can take this point. All zinc containing enzymes can be reconstituted by cobalt ion, and they do the same activity. But nature has gone for zinc because cobalt is not as readily available as the zinc ion on earth crust or water. These are the two sources nature chooses the metal ion, either on the earth's crust or available in the water. So then we got this master stroke, that is the straight line. Where I learned during my PhD that chemists look for a correlation always, and you go for it and you can check that Z effective by R, and it goes like that. So copper and zinc comparable, cobalt is nearby, nickel is really bad, and manganese is way down. So I have said why nickel is bad, it is written there. Because nickel has some directional property, nickel 2 has 2, 2, 2 and 1, 1. So some bonds will be formed this side, axial equatorial distinguished. But for the case of zinc, it won't take place because of the 10. So these we analyzed, and we provided this line to prove it. And this is the reason why zinc has always been preferred because of its abundant. But copper can be used also because copper is equally Lewis acidic. Now the condition is copper has a better weight for the things which is called the Jahn-Teller effect. I think I wrote in the next slide that copper has the formation maximum reactivity and adjustment between the Lewis acidity and levelity of metal ion. So if you only attack and it is not coming out, then you cannot do it. So you can have the reaction, it should come out also, both. And that way, copper is doing the job, at least because of its D9 Jahn-Teller effect in our system. Copper is slightly better value-wise, slightly better. Copper value is slightly better, but I won't consider that. But definitely they are comparable, no question. And now it is written there, so experiment I have already said, and we did the whole thing again and again, all those, and you have the data for the Michael-Menten plot, and you can see the values. The best bet, the efficiency, catalytic efficiency, best for copper in our system compared to zinc, but the worst is, nickel, and cobalt is better. Cobalt and zinc, they are comparable. And in our system, copper is the best because of Jahn-Teller, but nature does not go for it because of his redox problem. Is the main issue, I would believe. And this is what I have already written. What is that? You have to bind, but binding should be weak. If it's strongly bound, means your product won't come out. So nice balance is there. Association or KM values of this business plays a very, very important role. If the value is more, means binding is less. So 1 by association is the binding, Km. And then we did this physical chemistry little bit, EA, they're all comparable. Factor, these are all comparable. You can say delta dagger, delta S, and delta G. So everything is in order. Whatever you think, you get the same values. And you know why nature has gone for zinc and how it is possible. You have to understand the whole thing. And not only some inorganic chemistry does not mean you make a compound and something from paper. At least I don't believe in this. There should be a deep thinking and you can come out. I think this is the mechanism you can have when you are doing the alkaline pH. Then your medium has OH ion. So medium will take away this proton and then attack will take place. But when you are doing the neutral pH, then this for zinc, but this for copper is the right place. Because even the neutral pH, This guy will attack here, that guy will attack, and you don't need the extra weight ion. So for nickel, you need that extra weight ion. That's why UDS functions at an elevated pH. My time is up, or can I take 5 more minutes or 3 minutes? I'll just quickly give you one more. You know this primary coordination sphere and secondary coordination sphere. There's the metal ion surroundings and then the peripheral sphere. So we design a ligand. I'll very quickly scan through. It's a very nice bit of work, you will realize. I hope so. So this is the ligand we design. And what happens? You make a compound. You have a compound like this. You see water and you see water. And this is, Dr. Malla Reddy is very much here. So you see all kinds of non-covalent interactions. Don't pay attention there. But it helps a lot. Because of that, all this bond polarization takes place. It is not that OHO bond formation is fantastic. CHO is interesting. So this very thing, what happens when hydrolysis takes place. So this compound has this formula. That means 2 water molecules is 1 water, 1 water. So water molecule, 2 water, 1 water this side. So that water, you forget about it. This water and that methanol will do the job. Then we did it. And when you did it, we could see, you see this I never did before, you take the crystal of this, crystal of that, take the crystal, vapor-induced hydrolysis of ethyl acetate at room temperature. You don't have to give any temperature. Ethyl acetate we use to heat it up, otherwise you will never get hydrolyzed. This is a compound where at room temperature you just put a few drops and you will get hydrolysis of ethyl acetate. Not only ethyl acetate, but fluid. Then we have a pentamer formed. How? That this guy got hydrolyzed and generated ethyl acetate, acetate ion and ethanol, and it has been proved. Now in the process what happens, when you deproton, then a proton is generated, right? So it's the COET, means acetate ion, means there is a proton. What happens to the proton then? And what happens to that other one is ethanol. Ethanol is neutral. And you will be surprised that proton goes to protonate this phenolate. So this coordinated phenolate is acting as a secondary coordination sphere. Coordinated phenolate is becoming now wedge. That means elongated bond. Metal and phenolate bond distance you monitor. And after hydrolysis you monitor metal and phenolate bond distance. And you see bond distance is much more longer. One after another we have checked it. And this is the thing. And all the mechanisms, everything, and you see the distances which was 2.126 and previously it was only 2.062. So these increments always happen, and one of the NMET units, each ligand consumes proton, each turn remains uncoordinated. So they don't coordinate anymore. So we have done this kind of thing. Once you have it, say we have done the details of when you block it, what happens? Then the reaction should not happen, and it did not happen. When you don't block, it should happen. And if that is the one, what happens when you have the other kind of compound? So we did all details of it. And then you can say, sir, you are happy to show what is the space filling model is saying? A space is available. So when you take a crystal, put ethyl acetate, the ethyl acetate gets coordinated here, not at the other center. It is buried there. And then what happened? We proved it by infrared spectroscopy, the binding of the coordinated ethyl acetate, which was not there, and now it comes. We followed, and once you do it, then you can have also, I wrote it also, I forgot to mention, and there you have not ethyl but propionate. It does the same job. So not only ethyl acetate, you give me ethyl propionate, I will give you hydrolysis at room temperature, no alkali, nothing. And then we have this thing, understanding, and all those PK, FK determination we did, and this I have already repeated, and this is the science behind it, and that is the mechanism you can think of, that this water and it is having hydrogen bonding interactions. And when you coordinate that, attack takes place, and this proton liberated, it goes to the protonated form of your aliphatic amine or phenol. And this is what we published last year, that the detailed analysis of room temperature ethyl acetate in unactivated ester can be hydrolysis can be monitored, not only ethyl acetate but ethyl propionate and everything. So with this I have already mentioned, I don't have to say. I have done very little. This is an old picture of IIT Kanpur because the kind of hair you have right now, it is, I said Kolkata has made it more and more white. And you know, the whole thing, the work was done initially by this guy. He is very good in hydrolysis. And he learned hydrolysis from this guy in the faculty at IIT Kharagpur. So IIT Kharagpur did the first part of nickel. From him, he picked it up. And he is the source of all these. Other people, and this person, Himanshu, he made those compounds, manganese, cobalt, nickel, but did not do hydrolysis experiments. And he did some hydrolysis, but I am not presented today. These are all faculty members in various places. And this is the group Kanpur IIT and IISER Kolkata. You need some money and you need some source of money. So everything came, and I am grateful to all my co-workers because it is their hard work. Because of that, I am standing in front of you. And finally, I thank you for your kind attention. Thank you very much.
Professor Mukherjee once more. Now we will move on to our next lecture. This lecture is going to be given by Professor Graham Newton. So, Graham is currently a Nottingham Research Fellow at the University of Nottingham, UK. And before that, he served as an assistant professor in the University of Tsukuba, Japan. He has been a JSPS Fellow under Professor Hiroki Oshio at the University of Tsukuba. And he did his PhD with Professor Lee Cronin, who is a known name, as I mentioned also in the initial introduction in the scope of the course.